Hi, I'm Lee Teschler with EE World and Design World. I'm here with Joe Beck from Central Semiconductor, and we're going to talk a little bit about silicon carbide semiconductors. In the news a lot today. Joe's got a kind of a unique silicon carbide Schottky rectifier he's going to tell us about. It solved a couple of problems with packaging. Joe, what do you got there?
Well, as you know, at the show, Lee, everywhere you go, people are touting silicon carbide. It's become almost cliche. There's so much talk about silicon carbide, and the issues are quite apparent in terms of the solutions that people are trying to provide. Everybody wants to switch faster, and they want to switch higher voltages. So that's how we gain these great efficiency gains that people are touting. We're switching high voltages, we're switching them very fast. The problem is, you cannot just utilize a lot of the same packaging technology that's been used for a long time, especially when you get to these high voltages, 1200 volts, 1700 volts. A very common use for silicon carbide type rectifiers is either PFC or some type of switch mode power supply device. The challenge is existing package technology breaks down with those electric fields at 1200 volts. So you get creepage and all these kind of nasty internal leakages that really mess things up. Not only are we looking from a front-end wafer perspective for these new technologies, the packaging people now are having to go back to the drawing board as well. So a good example is the standard Zpack, which has been around a long time. People started putting a 1200 volt silicon carbide device in here, saying this is great, we're going to switch it really fast, we're going to bang it with 1200 volts, and it's going to work great. It doesn't, because the standard Zpack has 3 leads on it. The 2-leaded one just has the middle one trimmed off, but inside the package you still have all 3. So you're getting creepage, a voltage field across those, creating a real nasty effect. The packaging designer had to go back to the drawing board and say, how do we make this a truly 2-leaded device, even inside where you can't see? So we spread the field out. The electric field is neutralized or minimized. You don't get that creepage. The result is the customer's really, really happy. We call it a true 2-leaded Zpack. Another one that I can show as an example is what we call a TO257 package. Again, that's been around for a long time. We have some customers that want to use these at extremely high temperatures. So Central said, what's the highest rated temperature out there in the industry in terms of what people are speccing parts at? They're saying maybe 220 degrees C. We're going to be introducing a part that will operate at 250 degrees C. Again, you say, okay, this package has been around a long time, but the 1200 volt potential across it required some very unique construction inside this package, so that high electric field would be minimized. The result is a part that can sit for 1,000 hours at 250 degrees C with a bias on it, not have any breakdown or any nasty leakage effects, and it's wonderful for downhole applications, high temperature industrial, avionics, high temperature military switch mode power supplies. This is a great solution.
That's interesting developments, Joe. Thank you.
You're welcome.